Watch a modern cargo vessel load at a major port. It's a masterclass in spatial geometry. Every container, every break bulk unit, every steel coil slots perfectly into the holds to fill the available space. If you measure success purely by commercial metrics, maximizing physical volume and total deadweight capacity, this arrangement looks completely successful. The ship is full and the cargo is aboard. But beneath that geometrically perfect surface, a series of invisible, cascading failures is already unfolding. Microfractures are developing along the hull from stress imbalances. Incompatible chemicals are placed in toxic proximity. Up on deck, a shore crane stalls because the sequence demands a lift it physically cannot reach. This shows the danger of relying on plans that prioritize geometric fit while ignoring operational physics. A valid stowage plan requires an operational matrix that actively reconciles the static placement of cargo with the dynamic physical and chemical forces acting on the vessel in real time. This document outlines how independent surveyors test those connections. It details how a Stowage Plan Review Service provides a necessary technical check before loading decisions turn into stability failures, cargo claims, or severe port delays. Trusting a geometric plan without submitting it to this kind of rigorous operational review introduces massive hidden liabilities for owners, charterers, and insurers alike. To understand how these liabilities form, we have to strip away the outer hull and look directly at the vessel's skeletal structure under the stress of weight distribution. The most common structural fallacy in shipping is the assumption that a safe final loading state guarantees a safe operation. An acceptable condition at the point of departure does absolutely nothing to prevent or cure an unsafe intermediate condition while the ship is still at the berth. This graph illustrates the mechanics of bending moments and shear forces during a loading sequence. Notice the middle of the timeline. The red line tracking shear force spikes aggressively into a critical failure zone midway through the process, even though it ultimately settles back into the safe green zone by the time the final cargo is loaded. That midway spike is often triggered by poor sequential loading. Dropping heavy lift units or high-density parcels into the wrong holds at the wrong time applies immense localized pressure that the overall hull structure is not yet balanced to support. This uneven, asynchronous cargo distribution over the course of hours or days creates excessive trim and severe hull stress, risking structural damage long before the final pieces of cargo arrive. The mandatory countermeasure to this uneven weight distribution is continuous ballast sequencing, moving thousands of tons of water through the ship's internal tanks to counterbalance the incoming cargo. Looking at this split-screen visualization, we see a dangerous operational race condition. On the left, cargo tonnage is being loaded at a rapid rate by terminal cranes. On the right, the ship's internal pumps are draining ballast sluggishly. Mathematically, the ship's internal systems simply cannot keep up with the external loading speed. This race condition only worsens when local port restrictions, specific pumping capacities, or shallow draft limits further choke the ballast sequence, restricting the crew's ability to stabilize the vessel. Because of these complex variables, a review must compare the proposed plan against vessel-specific loading information. Relying on generic assumptions about a ship's class or deadweight is a direct path to structural failure. A ship's structural survival depends entirely on the synchronized choreography of the entire loading sequence. Time, in this context, is just as critical a factor as weight. Moving past the ship's macrostructural physics, we find a completely different set of risks buried inside the confined, localized environments of the cargo holds themselves. Severe cargo damage often begins before the ship even leaves the berth. Different cargoes interact physically and chemically, reaching right through what appear to be solid structural barriers. This cross-section shows the invisible threat of moisture migration. Moisture is evaporating from agricultural bulk stowed in Hold 1, traveling through the ventilation systems, condensing and raining down onto sensitive steel coils situated in Hold 2. Steel products are particularly vulnerable here. If a stowage plan fails to account for unverified dunnage, blocked drainage paths, or exposure to this kind of hold sweat, the resulting corrosion claims will destroy the commercial value of the shipment. The threat vector extends well beyond moisture. Placing a sensitive commodity too close to a high-odor cargo, risking dust contamination between holes, or stacking heavy goods on top of fragile packaging will systematically ruin cargo value. To manage these risks, maritime transport relies on strict regulatory frameworks, specifically the IMDG code for dangerous goods and the IMSBC code for solid bulk cargoes. The placement of any dangerous goods must be rigorously cross-referenced against these codes. Frequently, the mandatory segregation distances required by law directly conflict with the most efficient spatial arrangement on the stowage plan. However, even the most meticulous plan review operates blind if the underlying cargo declarations are inaccurate. Independent surveyors actively look for missing, inconsistent, or insufficient documentation. The goal is to identify these informational gaps early, forcing responsible parties to clarify exact chemical properties and physical sensitivities before the crane hook is ever attached to the cargo. Without rigorous, proactive segregation based on verified declarations, a structurally sound vessel can easily become a floating environmental hazard and a total commercial loss. Stepping out of the holds, we have to evaluate how the vessel actually interfaces with the external terminal environment, including the cranes and dockside logistics. When placing heavy, irregular cargo on the open deck, merely finding empty square footage is never enough. The selected location must directly match the structural capacity of the deck itself and align with adequate lashing points. This diagram illustrates the critical safety concept of blocked access. As this heavy lift unit is placed onto the deck, red zones flare up. The unit's footpoint has physically blocked a sounding pipe, a bilge well, and an essential route to firefighting equipment. A stowage placement can be perfectly acceptable from a structural and weight-bearing perspective, yet immediately fail operational compliance if it cuts off these mandatory inspection and safety routes. Furthermore, the securing method itself must be practical. A lashing arrangement that is overly complex or difficult for the crew to install safely while sitting in a calm port is virtually guaranteed to fail when subjected to rough seas. The realities of the terminal introduce entirely external failure points. Here, a shoreside crane attempts to load an oversized unit, but the booms simply cannot physically reach far enough across the ship's beam to execute the planned placement. Even when the equipment fits, the timeline often doesn't. A serious logistical conflict arises when the narrow window of time allotted at the berth does not permit the actual hours required for proper dunnage, securing, and trimming of the load. This is frequently compounded by unsequenced cargo arriving alongside the ship in an order that completely contradicts the carefully calculated safe loading sequence. A desktop stowage plan remains entirely theoretical until it proves it can survive the harsh physical constraints and logistical realities of the terminal berth. There is a massive operational divide between the pristine, static inputs on a desktop computer and the dynamic, highly unpredictable reality of a live port operation. This split screen demonstrates the concept of real-time invalidation. On the left are the original approved plan parameters. On the right, live ADA variables are shifting at the port. A late substitution, a wet hold, or a slight weight variance instantly causes the original assumptions on the left to flash red and fail. A single altered loading sequence or an inaccurately declared weight actively destroys the mathematical safety equations underpinning the entire plan. Because cargo operations change by the minute, higher-risk operations mandate physical surveyor attendance. A surveyor must be on deck during loading to compare the actual stow against the approved arrangement, exactly as it unfolds. This active monitoring produces an independent review record, which holds immense commercial and legal value. As outlined in this document, establishing liability requires concrete knowledge of the actual cargo condition, alongside its planned and observed positions. If a claim develops later, broad statements confirming the cargo was properly stowed are functionally useless. Resolving a dispute requires precision data, including time-stamped notes, detailed hold condition records, and documented securing methods. This highly detailed, immutable record is what protects P&I clubs, underwriters, and legal teams when allegations regarding damage, delay, or seaworthiness arise months later. A technical plan review, combined with live loading assurance, is the only proven mechanism to bridge the gap between commercial theory and operational safety. It is the definitive line of defense, protecting both the structural integrity of the vessel and the financial stakes of every party involved.